Hi there, in this video we're going to be continuing to talk about how we differentiate a quadratic form with respect to a vector. So remember in the last video we considered the quadratic form Q, which was equal to X transpose times our original matrix A times the vector X itself. And we said we gave an example where X primed was going to be a 1 by 2 row vector, A is a 2 by 2 matrix, and X is a 2 by 1 column vector. And we sort of did, using the rules of matrix multiplication, we actually found that this was actually going to be a scalar at the end. And we actually derived the form of what this explicit product was. It was just equal to A11 times x1 squared plus 2A12 x1 x2 plus A22 x2 squared. And then what we did is we talked about what it means to differentiate our scalar thing Q with respect to our vector X. And we said that it must have the same dimensions as our vector X, with the particular entries being, the first one being dq over dx1 and the second one being dq over dx2. And notice that this has got the same dimensions as X, it's just a 2 by 1 column vector. And then we went ahead and we actually found that this turned out, we could write this as 2 times our original matrix A times our row vector, or column vector X rather. And we talked about the analogy of why we've got this 2 out the front with sort of thinking about what happens when you differentiate y equals x squared, you get 2x. And this is kind of similar, but now we're thinking about matrices. So that's kind of why we've got the 2 out front here, because we're differentiating something which is in quadratic form. At the end of the video, I talked about we need to know what it means to differentiate Q, not just with respect to X, but what happens if we differentiate with respect to the transpose of X? Well, I hope by now it's not too difficult to understand what this means. It just means that we're actually going to get something which looks very, very similar to differentiating with respect to X, except it's kind of just going to be transposed. So the first entry in this row vector is going to be dq over dx1, and the second entry is going to be dq over dx2. So in fact, it's just this whole sort of thing up here transposed. So if we can think about it in that terms, well then all we need to do to find actually what this is, we don't need to evaluate it explicitly, we can just take what we found as the answer and transpose it. In order to do this, we need to make use of a particular result in matrix algebra, which is that if I have some product of matrices A and B, and I want to find the transpose of those two things, then this is actually equal to B transpose times A transpose. So the order of multiplication reverses after we've taken the transpose. So when we do this, the 2 just stays exactly the same. The only thing that changes is that the order is going to be altered. It's going to have X transpose times A transpose. But because A is a symmetric matrix, the transpose of the matrix is just itself. So we just get out 2X transpose times A. So these are the 2 results which we're going to use in deriving the least squared estimators, but in matrix form. I'll see you then.